Hello everyone. So today we'll talk about dissolved iron patterns impacted by shallow hydrothermal sources along a geotrace process studies transect through the Tonga Kermadec arc. This work is part of Chloe's Tiet PhD, and there is also a paper in GBC published in 2022 in the framework of the Tonga project. So let me take you to the Western tropical South Pacific, where a huge seasonal bloom almost the size of France is observed on a recurring basis. During the Outpace cruise in 2015, we measured huge iron concentrations in the low basin, up to 16 nanomoles, also corresponding to very high nitrogen fixation rates. We made the hypothesis that iron was coming from shallow hydrothermal sources from the shallow volcanic arc of Tonga. So following this, in 2019, we conducted with Sophie Bonnet another campaign focusing on the bloom area. One of the objectives was to understand the sources and sinks affecting this iron distribution in the Western tropical South Pacific, and to link these patterns to biological activity and carbon export. So we conducted 9 short duration stations and 2 long duration stations along the arc. The long duration station include additional short transect from shallow volcanoes to the deep waters. We collected and measured the total dissolved iron in 362 samples to determine its distribution along the transect using flow injection and chemiluminescence detection. So through a water mass analysis, we determined iron distribution due to water mass transport. From the measured concentrations, we deduced dissolved iron anomalies not explained by water mass transport. And finally, we identified the processes behind the longitudinal and vertical distribution of dissolved iron. And I will now go through these different points. So I present first the distribution of iron along the transect. The lowest dissolved iron concentrations were measured in the South Pacific Gyre, with concentrations around 0.2 nanomoles in surface. To the west, in the Melanesian waters, iron concentrations are still low, but higher than in the Gyre, ranging from 0.2 to 0.5 nanomoles in surface. In the low basin, iron concentrations are really high, both at surface and at depth, ranging from 0.8 to 50 nanomoles. And these high concentrations are visible, especially on the arc, as you can see on the small-scale transects performed at the long-duration stations 5 and 10. So we perform a water mass analysis inspired by the work that Lise Artig did for the Atlantic in 2020. And by defining the various end members contributing to the water masses crossed during the cruise, these are the circles you can see on the map, it was possible to establish the theoretical distribution of iron resulting only from water mass transport. And the optimum multiparameter analysis was used to establish the water mass contribution to the distribution of iron along the cruise transect. So these are the theoretical dissolved iron distribution resulting only from water mass transport, derived from the optimum multiparameter analysis, and you see they are very low and homogeneous across the transect. They are representative of classical oceanic profiles for each station, with low concentrations in surface, slightly increasing at depth. And this indicated a low impact of water mass on the dissolved iron distribution. Now, this figure represents the iron anomalies with a threshold of above 0.2 nanomoles, obtained by subtracting this theoretical dissolved iron distribution to the measured dissolved iron. So what we see is that to the east, the lack of anomalies demonstrates that there is no local source supplying iron to the waters of the South Pacific Gyre. To the west, in the Melanesian waters, except at depths at station 3, There are no anomaly greater than zero point 0.2 nanomole, meaning no local sources either. The most notable anomalies were found in the low basin, particularly near the Tonga arc. Strong anomalies are visible at surface, particularly near long-duration station 5, suggesting the presence of one or more local iron sources near this arc system. Hydrothermal origin of that iron was confirmed by the detection of other hydrothermal tracers such as helium-3, methane, CO2, manganese, in addition to typical chemical and acoustic features including low pH, low oxygen, high turbidity, and hydrogen sulfide contents. And you can see here, for example, the hydrothermal plume above volcano 1 at station 5, with a strong acoustic signal over the whole water column. So what about those anomalies at depths below 1,000 meters? We observe anomalies all over the basin, indicating a large dispersion of deep hydrothermal iron following the main circulation that is from east to west. There is also the possibility, of course, that those anomalies can be due to additional deep sources associated to the spreading area of the basin. In surface, in contrast to what has been observed for deep hydrothermal plumes, we see here a rapid decrease in the dissolved iron anomalies from the arc to the west over approximately 300 kilometers. And this is likely due to a shorter residence time of surface water masses, of course, compared to deep ones, combined with several biogeochemical and processes at play. So, what are those processes behind the vertical and longitudinal evolution of dissolved iron? So, what we did in that paper, for a simplified 1D 3-box budget, we were able to quantify the importance of those processes based on the observations made at a small scale that represents here a distance of 20 kilometers of the long duration session 5. Of course, I do not have to go into too many details, but in summary, what we found is that almost 90% of iron precipitates in the subaquic layer, that the scavenging, which is here in green, removed up to 72% of the remaining dissolved iron, that biological uptake in orange represented only a negligible iron sink in such high iron-rich environment. And in the upper photic layer, an additional sink of dissolved iron up to 36% was required to close the budget. So this could correspond to a higher scavenging rate in this layer due to the presence of the large proportion of biological particles, of course. But a portion of this sink could also be due to photoreduction. Alternatively, a combination of both processes, scavenging and photoreduction, could explain this additional dissolved iron loss. But these are only hypotheses, and more investigation are necessary to quantify both. So we did not discuss iron ligands in that paper as the data were not yet available at the time. But since several papers are dealing with the organic speciation of iron, explaining how this iron was finally stabilized in the upper layer. So I recommend in particular these two papers of the research topic in Frontiers, recently finalized. I also recommend the paper, the allied paper in Science, more focused on the link between hydrothermal iron fertilization and carbon export. So to finish, these are a few take-home messages. So first, unlike deep hydrothermal vents, shallow vents impact iron distribution over shorter distances due to stronger dynamics in the surface waters, combined with chemical, biogeochemical processes at play. This work also highlights the role of shallow hydrothermal sources on dissolved iron cycle. And despite the small but significant fraction of dissolved iron ultimately stabilized, there is a strong stimulation of the biological activity in the surface waters over a long distance. And finally, there is a need to consider the impact of these sources for a better understanding of the global iron cycle. And this is good news. We have a new project on hydrothermal iron fertilization, including the one from shallow sources. Project is named Harvest, and it will start in 2026. And with this, I thank you for your attention.